So let's finish this thing off. So this page summarizes the big picture. Last term, you solved this hydrogen atom with the Coulomb interaction between the nucleus and the electron. And then you can use spherical harmonics, Rm, YLM, theta phi, and then you solve that. Very nice. For example, this is the n equals 2 level. You have 8 states, 2 for S and 6 for P when you include spins. And then this term, we use quantum mechanics and we use some approximation tool. We handled spin orbit interaction. In a sample questions, you did the relativistic correction. You put everything together, you get equation 40, this one. And then the answer is that this will split into 2 levels according to the J. We have J equals half, we have J equals 3/2. This is higher in energy. The bracket 4 here means the degeneracy behind this level because Mj takes on 4 values, right? 3/2, half, minus 3/2. And we have 2 sources for J equals half. From the S, L equals 0, plus half, that is J equals half. From P, 1 minus half, there is half. So I put 2 origin here, and each has Mj equals plus half minus half. Therefore, altogether, we have 4, 2, 2, no more, no less, 8 states. Now, this is the level as far as we can get if we don't do quantum field theory. In order to explain the final thing, experimental data says there is a tiny difference between same N and same J. But this is 1 part in a million or so, and that is called the Lamb shift. By the way, Professor Liu Renbao, your teacher of the Quantum Mechanics 1, has been awarded the Lamb Prize this year by the International Optical Society for his contribution to quantum optics. So you are in good hand. You learn quantum mechanics from him. This is a big prize, an international level prize. So this Lamb shift, it is out of our scope to explain it. You need to learn more quantum mechanics called quantum field theory. This is also a summary of what we got. Last term, quantitatively, you got that. This term, we work out the form of this and take them as perturbation. We know how to do the integral, and this is the answer. And it is just off by the Lamb shift. That is beyond the theory scope. So let's summarize the technique we have been using. Very simple thing. We try to identify what is the perturbation term. We use the G factor. 2, we need some electromagnetic theory. We have some MC square discussion and ratio. We discuss total angular momentum and the rule, how to add them. Then we only use perturbation theory, nothing more than the thing in our toolbox. In hydrogen, we need this integral. Depending on situation, you may also want to do this. Then we compare with data, then we got pretty close result. So if you want to read more, you can read the quantum mechanics books. If you want to read more about the physics, you can read some quantum physics, modern physics book. I will give you a list of atomic physics books later today. So we were here before the break. Here is just a cultural page. What's next? If you want to learn more, what is the thing to learn? So up to what we did, the lamp shift was not predicted because we are doing quantum mechanics in whatever form, non-relativistic Schrödinger equation, relativistic Dirac equation, it doesn't matter, because in this quantum mechanics formulations, there's not the number of particles in the system is not allowed to vary. However, in many physical situations, for example, in accelerator physics, very often you collide proton, antiproton in CERN, you get a chunk of other things. So particles are being created and later on annihilated and become other things. Now, quantum mechanics, Schrödinger Dirac equation cannot handle that. When you have varying number, or some particles suddenly come out and then disappear later, we need quantum field theory. And in quantum field theory, for example, we can handle this situation. So for example, they are exchanging photons in quantum language, the Coulomb thing. That photon could occasionally become particle, antiparticle, and they annihilate into photon again, okay? So that popping up of particles, antiparticle pairs would affect the interaction a little bit. And that will give us the lamp shift. And that is a very famous calculation in QED in the early days. People like, I think, Hans Bethe, another Nobel Prize winner, did very accurate calculation using quantum field theory on the lamp shifts. So what's next? Now, this is cultural. This is beyond our course, don't worry. We mentioned that spin is a relativistic effect. So how can we do something on that further along quantum mechanics? What is relativistic quantum mechanics? The idea is that we have the Dirac equation. So Dirac wants to write down a quantum mechanical equation that is consistent with special relativity. So what he wanted to do is to do the following. Take the square root, then, but he doesn't like the square root, so he wants this square root can be done in some way. So he wants this at the end to be something like linear in MC square, but he needs something in front, and then to be linear in momentum. So he wants to look for these two things such that this square root can be written in this form. At the end, he found it. This beta and alpha stuff turns out to be 4x4 matrices. And the resulting equation is called the Dirac equation. So that is the next thing you may want to learn. And then the next thing that, well, this is for those who are highly motivated and want to go beyond undergrad quantum mechanics, okay? You need not do that at the undergrad level. You better understand completely what can be done within undergrad quantum mechanics. The next thing may be how to quantize an electromagnetic field. That is to say, you have the Maxwell equations. How can I turn them into a quantum mechanical equation? That will tell us how the nucleus and electron interact by exchanging photons. Photons are the quanta of EM fields. The next thing will be, after that, the next thing will be, okay, you have the Dirac equation written down. How can I further turn Dirac equation into a quantum field theory? That will be quantum electrodynamics. So for those who are very interested, at the end of some undergraduate level textbook, there's one chapter on that. So here I give you one example. And then for those who want a complete course on relativistic quantum mechanics and quantum field QED, this is a very readable book, but that is in the beginning postgraduate level, 600 pages or so. But if you understand 400 pages of them, you can actually do some calculation. There are many lines of equations in this book so that you can follow the calculation. Okay, that will take you directly to research level. That is as much as I will say about this further thing to learn. So for this, we are done with the spin orbit and its cousin, same order of magnitude in hydrogen, the relativistic effect combined it. The next thing will be to go back to the external field effect called Zeeman effect. So we have done Zeeman effect once, forgetting about spin there. We saw one line goes into three lines. It's called the normal Zeeman effect. But at the end of that section, I show you some experimental situations where one line gets into 6 lines. Sometimes one line will get into 10 lines. That is troublesome. How can we explain that? It turns out not to be difficult at all. In that discussion before, we ignored the spin. But now we know that spin is really there. So include spin into Zeeman effect. Okay, so that is the idea. We will do it again within our Schrödinger equation plus extra term and perturbation theory approach. So Zeeman effect is related to external field. But don't forget, there is always an internal field. This is spin-orbit interaction. Okay, so the situation will be quite complicated, but we can handle it logically. Now we have external field. We have orbital angular momentum giving rise to a magnetic dipole moment due to L. We discussed this and we got normal Zeeman effect. But now we have spin. Therefore, we have spin magnetic dipole moment that goes with S. We discussed that there is a difference of a factor of 2 here because the G factor is different. Okay. Nonetheless, you apply an external field. Each magnetic dipole moment will interact with the external field to give you an energy term. So this is the Zeeman due to orbital angular momentum. Lower one is the Zeeman due to spin angular momentum. So we have 2 terms, not one, plural, 2 terms. In addition, we have spin orbit. So we have the atom Hamiltonian, you know how to solve last term, plus 3 extra terms. So let's write it out. The Zeeman term related to the external field has two contributions: orbital, spin, magnetic dipole moment. Each term we know how to write it down. Minus mu L dot B minus mu S dot B. Okay? Again, different by a factor of 2 because G is 1, G is 2. Together, you factorize the external field, you have S plus L plus 2S. We emphasized last time, L plus 2S is not J, okay? Instead, it is J plus S because it's L plus S plus S, get me? So we mentioned that last time. Now, let's write down the whole Hamiltonian. We have the unperturbed part. We have the Zeeman term. Now, this equation, including spin effect. And then we also have the spin-orbit interaction. That is an internal field effect. All right? So this is related to internal field. This is related to external field. At this moment, we don't want to worry about the relativistic effect. It will make the story too complicated. So this term, I put it here with a bracket, and then I will drop it. Okay? That's okay for other atoms. Hydrogen, it depends. So all in all, we have this situation. Okay, so let me pause here. We have set up the problem for Zeeman effect. Do you understand why we have equation 43? Is that okay? We are putting our knowledge together. Is that okay? Okay. Is that okay? All right, good. Now, so we have a new situation. We have an unperturbed problem plus 2 extra effects. Then you may wonder what to do. Okay, should I take this first, do it more seriously, and then do this as perturbation, or take this, do it more seriously, do this as perturbation, or both as perturbation, or what to do? Okay, now good questions, and then we have to answer it logically. Which one to do first? The answer is depending on the situation. There's no standard answer. For the reason, we have two terms. One is related to the internal field, spin orbit. One is related to the Zeeman effect, external field. Okay? If your external field, you can buy a 10 tester or 18 tester magnet, then your external field may be bigger than the internal field. So one term will be more important than the other. If you are poor in your lab, you only have 1 tester field or 0.5 tester field. The internal spin orbit one is already bigger than your external field. So you do the spin orbit first and the Zeeman later. So a logical approach, think like a physicist, is that it depends on how big the external field is compared with the internal field. That is a makes sense answer, right? So the big picture is, if you have strong external field, then Zeeman is important. You do this part more accurately. Try as best as you can. Don't make too much approximation, all right? And then do this as a perturbation. Just rough estimate for the last effect. If the external field is weak, spin orbit is more important. Do this part first and take that as a perturbation. Recall, if this is the important thing, we know how to do. Use the JMJ, we just did that, okay? So we have two limits to consider: strong field Zeeman and weak field Zeeman effects. The most typical thing is that they are of the same importance. Oh, what to do? Logical answer is very difficult to do. But then think, maybe we can set it up as a matrix problem, call a subroutine to diagonalize the problem. Still work, numerical approach, all right? But in our course, we want to play with our toolbox and extract the physics, look at the physics. So we have these two approaches. So do you follow the logic? Strong field, do Zeeman first. Weak field, do the spin orbit first. Do you get the concept? Get the idea? Okay, so let's move on. This is a big picture way to think about the consequences. Strong field, we do the Zeeman thing first. Okay, we see the LZ operator and the SZ operator thereby. If this is more important, we should stick to the spaces, the description using the Z component of orbital and spin angular momentum, ML and MS spaces, not to add them into total, because this set will be readily fit to handling the Zeeman term. Okay? If the field is weak, the external one, spin orbit is important. When we see this L dot S, immediately our mind goes into the JMJ. Now, if you turn on this external field, this MJ degeneracy will be split. And you started to see even number of splitting that will give rise to even number of lines. There is some hope we can explain the enormous Zeeman effect. 異常嘅 Zeeman effect. Okay, so at least at this early stage of the discussion, we started to see through the problem. So the moral of the story is that when you have many things to do the more important things first. So obviously coming to class is not one of the important things. So we have two things. Pick the more important term, do it rigorously. The remaining one, try some first order perturbation. So let's start with the strong field Zeeman effect. What is the unperturbed problem? It is the hydrogen atom or any atom problem. You solved it before. So very formally, this is the part you solve. Quantum number n, principal n, and then you have L, ML as YL, M theta phi, the angular part of your wave function. The last two indices are the spin of the electron. For an electron, S is always half, but I would like to keep it there for completeness. You have ms plus half minus half. Usually people call it spin up, spin down. You have a wave function for it, which is a spinner, 1, 0 for Z component being up, or 0, 1 for Z component being down. So whatever way you represent it, it is the matrix representation that I mentioned. This is the spin part. Okay, so we have some common ground. So this is the eigenstate, or these are the eigenstates of the unperturbed atom Hamiltonian. And the energy in general is labeled by N and L for central force potential. Hydrogen is a special case. It only depends on N. So this is the old knowledge. That's our starting point. The first thing now is strong external field. The more important term will be the Zeeman term. Subscript Z means Zeeman. Okay, so the Zeeman term is of this form. We already discussed it. When we see we have LZ operator and SZ operator in the Zeeman term, we should be happy because we don't need to do anything. This set, same set, when LZ operate on it, it will look for ML. When SZ operate on it, it will look for MS quantum number. Therefore, this set are automatic eigenstates of the Zeeman term. Let's see. LZ operate on this thing. Next page. LZ operate on this thing. Orbital angular momentum YL theta phi. Look at the ML. It will pick up this Z component. For the spin SZ operating on the spin part, if it is up, it will pick up plus half H bar, that is to say the quantum number plus half. When it is down, it will pick up minus half. Okay, go back. So perfect. This add on this quantum number give us ML H bar. This add on the spin part, pick up 2ms because there's a 2 here, H bar. Factorizing the H bar out, this is Bohr magneton, mu B, right? Okay, so all of a sudden in one line, we did the Zeeman term exactly because we have found the set of eigenstates for the Zeeman term without changing anything. That is what I meant by do this part more seriously. This is really seriously. We already did the part exactly. Okay, so the answer is the unperturbed energy. I'm using hydrogen as the example. And then the Zeeman term will have the effect of mu BB that defines how much the splitting will be. This is an energy. And then times the number of order 1. ML plus 2ms. Okay, so I pause here to see whether everybody understands that we have done the Zeeman part rigorously. Okay, you follow? Although we are not done yet, but this is a big step. Okay. All right. Good. So now we should be happy. Okay, no perturbation. We did that. So now we have a smaller term to worry about, the spin-orbit interaction. Well, given that this is the more important one and we already did this thing exactly, we have the basis function to do first order perturbation. Since this is secondary, less important, we believe first order perturbation is all right, just a tiny effect. We have done the big part, all right? So now recall, spin orbit has a form that goes like S dot L and then a function of R in front. Very complicated thing, 1 over R, dV, dr, things like that, but function of R nonetheless. First order perturbation. You take this wave functions, try to get the expectation value. So on the right, on the left, the same thing, integrate over every coordinates. Here, it is integrating over r theta phi. Mr. Choi, the answer is yes to your question. Okay. And then this d tau means two things actually. We have to integrate over r theta phi for the spatial coordinates. And then when we see S, the spin thing, operate on the 2n, the spin thing can be written as a 2 by 2 thing, right? Depending on Sx, Sy, Sz. And then on the two sides, you have the spin part. They are spinners. So on one end, it is a column. On the left-hand side, it is a, you put the two column, you put the column flat. So you have a 1 by 2 times a 2 by 2 times a 2 by 1. Okay, so it means this whole thing integrate over all coordinates. But as you see, it is easier than that. Okay, so the first line is formal. This is first order perturbation. I hope that at least you know what we are doing. Okay, now let's manipulate. Dot product means this. All right. Now I would like to claim this is 0, the expectation value, and this is 0 as well. Okay. Now, very easy. I think in your last semester's final exam, you have a lot of this thing to do. If it is a Z spin eigenstate, you look for the Sx expectation value, it is 0, right? Okay, so this is either up or down in Z. So when you do this Sx expectation value, it will give you 0. Then I don't need to argue that this is 0 as well. Okay, one thing is 0, the product is 0. Okay, now if you forgot about this, let me show you exactly what it is. Now you have an x. This is Z up eigenstate. This is expectation value. You multiply everything, it is 0. Okay? Or more qualitatively, you have an Z eigenstate. You fly it into the Stern-Gerlach experiment aligned as x direction. There will be 2 beams coming up, coming out, 50% bend this way, 50% bend that way, meaning 50% will have Sx is plus half, 50% minus half, the expectation value is 0. That is a more physical argument. Okay, if you don't like physical argument, you like mathematics, this is the argument. Okay, now similarly for Sy, this basis is related to the Z direction spin eigenstate. You ask for the Sy expectation value, it is 0. So pretty nice. Although dot product gives you 3 terms, 2 terms are zeros. Of course, more rigorously, you can also argue that this expectation value for the angular part is also 0. As this week, the TA will demonstrate this point to you in sample question number 11. So all in all, we are left with this term, expectation value. Okay, that's easy. When SEZ hits this thing, this is MSH bar. When LEZ hits this thing, it is MLH bar. Oh, first order perturbation is easy to do. The spin orbit part will give us this combination from the EZ dot product. And don't forget, this integration has a radial dr, r squared dr integral to do. That I don't want to write it out explicitly, so I leave it as an expectation value of the radial wave function and with the spin orbit interaction p factor inside there. Okay, it is a number nonetheless. So we have treated the first order perturbation. We have treated the spin orbit interaction within first order perturbation. So let's put the results together. Strong field. We do this first. We found that the bases using MLMS are automatic eigenstates of this part. Thereby, this part is treated exactly. We use these spaces to do first order on the spin orbit part. We got this result. One integral left to be done. Nonetheless, that can be done usually for hydrogen. So we have this full result for strong field sigma. That is the mathematical treatment. I want to demonstrate the things in our toolbox are already very effective. You don't need to learn a lot more. Okay. Next, we would like to analyze the consequence, the physics. Very interesting thing will come out. Now, let's consider a P state, for example, 2P. We know that P is L equals 1. There are 6 states, right? ML is 1, 0, minus 1, and each one can be up, down, so 6 electron states. So let's get ready for that. ML can be 1, 0, minus 1. MS can be plus half, minus half. So there are 6 combinations, right? So here I list the 6 combinations. Okay. To prepare for using the form, the answer, we need this combination. Okay. So we can do that. ML plus 1. 1 plus 1 is 2. Okay. Do you understand? So similarly, for all the 6 combinations, I got these numbers. Okay. To prepare for handling this term, I take the product, ML times MS, so I put it there. All right. So similarly, I get these 6 numbers. Understand? So now I'm ready. I know this, I know that for the 6 P states. The next page is important, the consequences. At this point, let's handle the bigger part, strong field. If we ignore everything, atom part, p states, there are 6 of them. So I draw 6 states at the same energy. All right. Now, let's consider strong Zeeman only. So we have this thing. We work out these 6 combinations. This number is 2, 1, 0, 0, minus 1, minus 2. All right. Therefore, I have 2 mu BB, 1 mu BB, 2 state not changed, 0, 0, minus 1, minus 2. Okay, so do you understand how this comes about? Okay, the highlight part is the important part because strong field. Understand? Okay. Now let me tell you, this is the P state. You can do the S state, 1S for example, and you will see that will go into 2 levels. Okay. You have spin equals plus half minus half. Okay. And then you have 5 different energies up there. You have 2 different energies down there. And then you can count how many transitions, how many lines you will see. All right. Of course, there are things called selection rules governing which one can go down to which one. The rules about transitions. Interestingly, in this strong field case, you will see even you have 5 transition down to 2 levels, there are only 3 different frequencies. Thereby, 1 line goes into 3 lines. This is still normal Zeeman effect. The even number of lines has to do with the weak field Zeeman effect. Okay, so stay tuned later. But here, do you understand this box? Okay. Now, for the fancier student, you want to take into account of the weaker effect, spin orbit as a perturbation. Fine. We have worked this thing out. Notice there are 2 zeros. That means the spin orbit has no shift at all for these 2 states. So let me draw it out. The first state goes up a little bit. Okay, there's a factor here. We haven't calculated it, but it is perturbation. The shift cannot be big. So it will move up a little bit by this amount. And this amount is defined as such. Okay. Now, this state is a 0. So there's no shift. The 2 states here, degenerate, they will move together. So they remain degenerate. And this has no shift, and this is shifted the other way. Okay. So this is the effect of including both the strong field Zeeman and the weaker shift due to spin orbit. So we have done this strong field Zeeman effect in a very logical and technical way. Okay, so let me introduce the name. I don't like jargons, but for some who will be going into atomic physics in your final year project, etc., you may encounter this name. In atomic physics, the strong field Zeeman case is usually called this Perchen-Back effect, following 2 names. Okay, and as I already mentioned, if you analyze 2p to 1s transitions, you still only see 1 line go into 3 lines. So we have yet to explain the enormous Zeeman effect. It is still the normal Zeeman effect, even you include this spin orbit as a perturbation. But that's natural. The difference between our discussion in this part and the former discussion is that we included spin magnetic dipole moment. Therefore, we have two terms. We have this additional thing in the Zeeman effect. Nonetheless, this will not give us more lines. It only changed the number ML in the previous discussion to a combination. Okay? So that's interesting. It has more splitting, but due to selection rule, it does not give us more lines. Okay? So I think I will stop here today. We have one more thing to go, and then we will go to the hyperfine interaction next time on the tiny effect. It is 10 to the minus 8 eV effect, okay? Even smaller than 10 to the minus 5 here, all right? So I will stop here today. I will stay around. If you have questions, you're most welcome to raise them.